Today we will be simulating a capacitive pressure sensor, both with and without stresses induced by the packaging. The geometry of the sensor is symmetric, so only a single quadrant is modelled. The sensor consists of a thin chamber sealed under high vacuum, acting as the dielectric in a capacitor. It is separated from the ambient air by a thin membrane, which is electrically isolated from the grounded body of the sensor. We will investigate the deflections of the membrane due to both ambient pressure changes and thermal stresses resulting from a poor choice of package. In both cases, the deflections are detected by measuring a change in the capacitance between the membrane and ground. To begin, we select the model wizard and then choose a 3D space dimension. Next, we add the Electromechanics physics interface. From the preset studies list, we choose the stationary study. The first step is to import some model parameters which we'll use to specify variables within the model. Click Parameters and then select the desired file. Here you can see there are 3 imported parameters. P0 is a pressure. This is the ambient pressure at which the device is operating. And we have 2 temperatures, T0, the ambient temperature at which the device operates, and a reference temperature, Tref, which is the temperature at which the device is bonded to its package. Next, the geometry is configured. For convenience, the geometry is imported from an external file. To do this, from the Home tab, select Import, choose the desired file. Here you can see we've imported a pre-made geometry which is 1/4 of the device we are modelling. To simplify the configuration of the physics interface and to aid with post-processing of the results, it is convenient to now define some coupling components and some geometry selections. Two coupling components have been added. An average operator, which operates on boundary 12. Boundary 12 corresponds to the underside of the silicon membrane. So here we have the silicon membrane, the cavity, and the silicon die. And you can see highlighted in blue the underside of the silicon membrane. And an integration operator, which integrates one point. This point is the point where we expect the maximum deflection. It's right in the center of the underside of the membrane. We've also created a collection of boundaries which make up the YZ symmetry plane and a collection of boundaries which make up the XZ symmetry plane. These will be used when specifying the symmetry boundary conditions in the physics interface. All the domains which make up the steel base have been selected. This is useful when we assign the materials to the model. Explicit selection has been used to select the cavity domain. So this is that vacuum cavity between the silicon membrane and the grounded body of the sensor. A second explicit selection has been used to select all domains, and then a difference operator has been used to remove the cavity domain, leaving a selection which is everything except for the cavity. This will be useful when assigning the linear elastic material properties later. Next, we add the physics settings to the model. These include the pressure forces acting on the sensor, the applied voltages, and other appropriate domain and boundary conditions. First, we add a linear elastic material node to the Electromechanics physics interface. From the Physics ribbon, we select Domains, Electromechanics, Linear Elastic Material. Here we can use one of our selections created earlier. We can assign the linear elastic material to the linear elastic selection, which encompasses all domains except for the vacuum cavity. Next, we can apply the symmetry boundary conditions. From the Physics ribbon, we select the boundary conditions, and structural, we choose symmetry. For the selection, we simply choose one of the symmetry planes we created earlier. We then repeat the process and select the other symmetry plane we created earlier. Next, we need to add a prescribed displacement to a point on the model. The physics ribbon we choose from the points, and from Electromechanics, prescribed displacement. You're going to apply this to point 44 only, which is this corner point here. The reason we apply this boundary condition is to constrain the position of the geometry in the z-axis, and this will prevent COMSOL from searching for solutions in which the whole geometry is translated arbitrarily up or down the z-axis. So to do that, we click prescribed in the z direction and we leave the default 0 here. So now the structure is pinned in place in the z coordinates, and although it can deflect, it can't translate in its entirety. Next, we need to add a boundary load condition. This is used to apply the pressure to the device. From the physics ribbon, we select boundaries, and from structural, we choose boundary load. This is applied to boundary 13 only, which corresponds to the top of the deflecting membrane. We're going to set it to take a pressure as its load type, and we're going to set the value of the pressure to P0. Next, moving mesh boundary conditions must be applied on the boundaries adjacent to the cavity. This will allow for the mesh to move as the surrounding material deforms. From the Electromechanics interface, we select the prescribed mesh displacement node. And here we clear the prescribed Z displacement, which allows the mesh to move up and down in the Z direction as the membrane deflects. Now we specify the electrostatic boundary conditions required. From the physics ribbon, we choose boundary. From electrical, we choose terminal. This terminal boundary condition is used to apply a voltage to the underside of the silicon membrane. Select boundary number 12 again, and we're going to change the terminal type to voltage, and the default electrical potential of 1 volt is sufficient. Next, we once again return to the boundary conditions and the electrical section, and we select ground. And this we want to apply to the top of the silicon die directly below the cavity. So we choose the corresponding boundary, which is boundary 9. So if we zoom in, we can see the selection of these electrical boundary conditions. So you can see that the voltage of 1 volt has been applied on the underside of the silicon membrane, and the ground has been applied on the other side of the cavity. Now that the physics has been configured, it's a suitable time to apply some materials to the model. From the Home ribbon, select New Material. You can see that the new material by default is applied to all domains, and COMSOL knows which physical properties are required for the model to compute. The first material we shall rename silicon, and we'll use it for the silicon part of the model. Enter some values appropriate for the silicon material. Next, we add a second new material. This material is going to be added only to the cavity. Here, COMSOL knows that in this domain, all that's required is the relative permittivity, which we set to 1 to represent the vacuum. Finally, we can use a built-in material to specify the steel domains. From the Home ribbon, we click Add Material. From the built-in library list, we select Steel. Apply this to the steel base selection we made earlier. Notice how the materials override each other as they're subsequently added. So initially the silicon material was applied to all domains, and now it's overridden by the vacuum and the steel in the appropriate domains. Next, we set up a structured mesh to solve the problem on. On the Mesh ribbon, we select Edit to allow us to edit the default physics-induced mesh sequence. Rather than the default free tetrahedral, The geometry here calls for a mapped swept mesh. First, we disable the default free tetrahedral. We would like our mesh to be densest around the region of interest, which is the membrane that we expect to deflect. To do this, we add a size node and select custom, and then specify a maximum element size, 50 micrometers. Apply this to a boundary. We're going to choose boundary 3 only, which you can see is this boundary on the bottom of the device, which marks the cross-section of the membrane. Now we add a mapped mesh to the lower surface of the model. Choose boundaries 3, 16 and 32, which make up this bottom surface of the model. And here you can see that the smaller maximum size node has reduced the area of the surface elements in this region directly below the deflecting membrane. And then we have nice sweeping radial mesh elements. Then the final step is to sweep this mesh up along the z-axis through the structure. So we add a swept mesh node, build all, and there you have it, a nice structured mesh suitable for this geometry. Now that the parameters, geometry, physics and mesh are all configured, we can prepare the study. We will configure the study so that it sweeps over a range of applied pressures so that the response of the sensor can be assessed as a function of the ambient pressure. Within the study node, we find study step 1 stationary and expand the study extensions section. Here we can check an auxiliary sweep and add the P0 pressure variable. You can choose an appropriate range. Now that the auxiliary sweep is configured, from the home ribbon, we may compute. The default plot shows the total displacement. It is clear that much of the structure is not displaced at all in this initial study. In order to quantify the displacement, we can use the 2 coupling components that were created earlier. From the home ribbon, we want to add plot group and choose to add a 1D plot group. Now we want to add a global plot, and first we can use the average operator. So this will take the average of W, which is the vertical displacement, over the avop boundary, which was the underside of the silicon membrane. Select micrometers as a more appropriate unit. And we can use the point integration operator to allow us to plot the maximum displacement. Now we can tidy up the plot a bit. You'll see here I've renamed this 1D plot group to membrane displacement, and this shows the displacement of the membrane as a function of pressure. I've added a title for the plot and labelled the axes. Now we can plot the capacitance as a function of pressure. Once again, from the home ribbon, we select add plot group, choose a 1D plot group, and a global plot. This time we choose the capacitance variable, which is output automatically by the electrostatics interface. Picofarads is a more appropriate unit. Now we can tidy up this graph a bit. And here we have created our plot for the capacitance as a function of pressure. I've added a title for the plot, labelled the axes, and moved the legend to the left side of the plot. Now that the stress-free study has been completed, we can add the effects of thermal expansion to the model. In the Electromechanics interface, we right-click linear elastic material and choose the thermal expansion subnode. We set the temperature of the device to the parameter T0, and we set the reference temperature, which is the temperature at which there is 0 stress due to thermal expansion, to be Tref. which is the temperature of the device when it was packaged. Now that we have added additional physics to the physics interface, we see that the materials section requires additional parameters. Specifically, we need to enter the coefficient of thermal expansion for the silicon. Note that the steel, as it came from the built-in model library, does not require us to add additional coefficient of thermal expansion, as this was already available. In order to include the effects of the additional thermal expansion without overwriting the initial solution, we add a second study to the model. From the study ribbon, we select Add Study, and we add a second stationary study. Once again, we need to configure the study to perform an auxiliary sweep over the P0 pressure parameter. Enter the same range as before, and then we can compute. Once again, the default plot shows the surface displacement. Notice now that the entire structure is displaced as a result of the differing rates of thermal expansion between the steel base plate and the silicon device. To compare these results with the first study, we can add the new solutions to the same plot groups. Duplicate this global plot and then change which solution it gets its data from. Tidy up the graph a bit. So the solid lines correspond to the initial study with no thermal effects, and the dotted lines show that with the thermal effects there is an increased deflection for a given pressure. For this plot, I move the legend out of the way and change the line style for clarity. I can do the same for the capacitance. I can duplicate the original plot, change the solution from which it gets its data, and tidy the graph up a bit. And here we have created our plot for the capacitance as a function of pressure. I've changed the line colour and made some minor changes to the data labels in the legend. And you can see now that the response of the capacitor to pressure is very different now that the effects of thermal stress are included in the simulation. Learn more about this and similar models at comsol.com/models.